A square loop of wire, 0.3 meters on each side, has a resistance of 0.5 ohms. The loop is moved at a constant speed in 0.6 seconds from position 1, where the magnetic field is 0, to position 2, where the magnetic field is 1.5 Tesla. What is the magnitude of the induced EMF in the loop during this time? What is the direction of the induced current in the loop? What is the magnitude of that induced current? What is the power dissipated in the loop? And how much force is required to move the coil from position 1 to position 2? What is the magnitude of the induced EMF? Well, we use Faraday's law of induction right here, and the negative sign being Lenz's contribution. We substitute flux is equal to BA because the magnetic field is perpendicular to the cross-sectional area. And then what is A? A is just the area of a square, which is S squared. So here we have our algebraic expression. Our final magnetic field, here's 1.5 Tesla, and typically, or almost all the time, change is always final minus initial. The initial was 0, there's no magnetic field out here, times the area of the square, which is 0.3 meters squared, and it was all done in 6 seconds. We're taking the absolute value because we want the magnitude, and we get 0.225 volts. What is the direction of the induced current in the loop, as it's there in the field, okay? The wire moves from an area of no magnetic field to an area where the magnetic field is out of the page. The induced current has to create a magnetic field to oppose that change in flux. So how do we do that? There's all these out of the page vectors, so we need to create magnetic field into the page, right? This is Lenz's law. So how do we get that? We use the right-hand grip rule, and if we stick our thumb over here, and here's the rest of our fingers, and pretend to grab the wire, we find that that generates a magnetic field into the page, which is exactly what we want to counteract the increasing flux out of the page. So what kind of current flow is that? That looks like clockwise. Now we want the magnitude of the induced current. Well, we have the voltage and we have the resistance. And again, EMF, voltage, same thing in this condition. So we have 0.225 volts over half an ohm, and we get 0.45 amps. What is the power dissipated in the loop? Well, power is IV, among other things, but here we have the current and the voltage. We might as well use it. There's the current, here's the voltage that was calculated, and we get 0.101 watts. You could also use these two expressions too if you'd like, get the same answer. How much force is required to move the coil from position 1 to position 2? Well, we use the magnetic force equation, F equals ILB, or Philb, where L is the length of the coil that's exposed to the magnetic field. So as you're moving in, the only thing that counts is this one. And you might ask, well, how about this guy and this guy? Well, in that case, since the current's going in opposite direction, those forces will cancel out. So you don't have to worry about that. So the length, we're going to use 0.3 meters. We're just going to take into account what's happening with this guy moving through the field. And we have the current, and we have the magnetic field. Plug the numbers in, we get 0.203 newtons.